All right. Yep. Sounds good. All right. Hi, everyone. Thanks for having me. So I'm going to talk today about stellar corona. Yes. All right. So I don't think I need to tell this audience why we care about stars in general, coronas in general, or magnetic fields of stars in general. But what I'm going to specifically talk about is why the coronal magnetic fields of a star affects not only the star itself, but the stellar system. It affects any particularly close-in companions, and because of that, the size of the corona matters. But it's a challenging problem to detect magnetic fields above the surface of a star. And so that was the birth of this project, which was some observations by Clement et al. And John Clement is in the audience, so he can tell me when I'm getting things wrong. So what we have here is some VLBI, so very long baseline interferometry of the star AB Doradus. And that is right here. So this image is showing the two lobes of emission that they found that are pretty far from each other and far from the star, so 8 to 10 stellar radii. And in this image, the bit you want to look at are these red contour lines. The background is the point spread function of the telescope, so the emission is here. And this was an observational paper. And so they put forth a number of different possible physical scenarios that could lead to the observations that they see. And here's one of them. So this is a bit of a spoiler alert for the conclusion of the talk. But it's showing that the idea that what we're seeing in these emission lobes is evidence of plasma at the top of large magnetic field loops that are more or less above the equator of the star in a magnetic sense. And so we thought, well, can we figure out which scenario is right and what's actually physically happening here? And the reason we thought we could do that is because we also have ZDI imaging of the same star from the same year as some of the VLBI data. And happily, I don't have to tell you about ZDI because several other people have. But the point being, we have a surface magnetic field map of this star that we can use to build a model that we can compare with the radio data. Before I continue, what is this star that we are looking at? So it's about solar mass, radius, and temperature, but it is much younger than the sun. It's just sort of approaching the main sequence. It also rotates very quickly, about 50 times as fast as the sun. And it's nearby, 15 parsecs, which doesn't affect the star, but it does mean it's easier for us to observe, which is great for doing these kinds of studies. So what I'm going to do is to model just the corona. So from the surface of the star up to the extent of the corona. And I'm defining the extent of the corona here as the imaginary sphere beyond which all field lines are open. So within that, we have closed magnetic field lines and open magnetic field lines. And beyond that, everything is open. And this is going to be, this is a different definition than, say, looking at the Alfvén radius, and is typically going to be inside that. So what I give to the model is the boundary conditions, of course. So the base boundary condition is that surface ZDI map. And then the upper boundary condition is a geometric boundary condition where at the corona extent, we insist all field lines are perpendicular to that imaginary sphere. We also give a corona temperature and a base surface pressure. And what we get out of this model is the magnetic field strength everywhere and the density everywhere. And so given those values, we can then trace closed and open field lines through it and get something like this, which is the closed magnetic field lines for this model with one specific set of parameters. We also traced open field lines, but I don't show them here. And this is a three-dimensional model that we can rotate as we please. And then we can take this and use that to make synthetic images that we can start to be able to compare to observations. So to do this, I rotate the model to the desired viewing angle. and then take sight lines through it, modeling the quiet background radiation. So here I take into account the opacity and the free emission, and then we get something like this rotating two-dimensional image. And here I've annotated it with our boundaries, the stellar radius and the corona extent, and also the co-rotation radius. And I point out the co-rotation radius because this is the radius beyond which rotational effects start to matter more. And I just want to point out how much of the closed corona is beyond that point. So these effects do become important. But this isn't something that we can compare to the data yet. We can create these images with this level of detail that our telescopes just can't see. So I convolve the synthetic image with the approximate beam size of the telescope for VLBI and this star that's about 5 stellar radii. And I get the blue and purple image here, which looks a lot less detailed and a lot more blobby, but also a lot more like the actual data. So on this slide, I'm showing the top row is the data plots from the Clement et al. Paper, and the bottom is my model output. And the way I'm getting all of these geometric morphologies that the paper found is just the rotation of the star. So we can rotate our model to the inclination that we know AB Dor has, and then we can rotate it through our phase, and we can recreate both the two-lobe images, the sort of two-lobe squished together images, and the one-lobe image, which is wonderful. It looks great, but that's not enough. We need to be able to compare this in some actually quantitative way. So we compare along two axes. The first one is probably pretty obvious. We get a total flux measurement out of our model, and so we can compare that against the observed flux and see if we're getting the right amount of intensity out. And we also compare the distance between the two-lobe structure when there are two lobes, so we can see if we're getting geometrically something that not only looks the same, but is of the correct size. And I do this across a grid of models, so varying the temperature, varying the size of the corona, and varying the base pressure. If I fix to one of the temperatures we test, 9 million degrees for the corona temperature, and I look at the models varying the corona extent and the pressure, I get this, this distribution. The black line, contour line, is showing the area of agreement between our model and the observations. And we can see that there's a range of corona sizes and pressures that will give the correct flux. If we also look at the contours for the peak separation, so here the black area is showing the models where at no rotation do you see more than one lobe of emission, so we can't get the correct geometry at all. And again, the black contour shows the area of agreement with the models. And if I plot just those areas of agreement together, we have a really nice overlap where we have a clear best model. And if we adjust where we think the agreement is, we still continue to get one small bit of agreement. It just varies where it is. So it's robust against errors in the observations. But this is only one temperature, and we tested a bunch of temperatures. So here I'm showing the gray areas and pale areas in the back are those areas of agreement for every temperature. And then the colored contours are showing the contours of agreement along both axes, so corona size and pressure for every temperature. And we can see that there is a bunch of these contours that overlap and then two outliers. So those two outliers are our lowest temperature models. And there are areas of agreement for them, but they don't fit with everything else. But once we get up above about 4 million degrees Kelvin, there's this sweet spot where we are no longer dependent on temperature, and all of the models agree that you want a pressure of that's pretty comparable to solar pressure, and you want a radius corona size of about 8.5 stellar radii. So that's quite big, but it is consistent with other estimates for young stars. And it does mean that we have to think about the possibility of companions and planets orbiting within that size. Sebastian, who was talking earlier, at a very different kind of star, so it's not going to have the same corona. But that planet was orbiting at 2 days, whereas a planet orbiting just at the edge of this corona would be orbiting at 3 days. So there really is a possibility of getting planets within this, and that would affect the environment of the planet and its interactions with the star. So my conclusion is that we can use this multi-wavelength technique to get information about the size of the corona. We've done it for AB Dor. All we need is more of this data to do it for other stars. And we know now that AB Dor does have an extended corona as predicted, and that is probably going to be true then of other similar stars. Thank you.
Great talk. My question is, which emission mechanism? Your name, Jeffrey Linsky, University of Colorado. Which emission mechanism are you assuming? Free gyrosynchrotron emission, and how did you come to the conclusion of the mechanism that you're using?
All right, thank you. That's a great question. So the question is, what emission mechanism am I assuming, and why am I assuming it? So I'm assuming it to be free. I'm looking at the quiet background radiation, nothing that is transient. And the reason that I'm assuming that is because the radio observations show persistence of these features over long periods of time. So we rule out short-term transient effects like flaring. Yeah, that's basically it. There's a couple of other mechanisms that we ruled out because they don't appear in the wavelength regimes that we're looking at.
From Astro. Great work, Clara. Something I was thinking about was, have you thought about doing a stellar wind simulation for this? Because this is obviously going to alter the stability of these stars, those field loops. Any plans to do something like this?
All right, so the question is, do I have plans to do a wind simulation? So I did, because they would destabilize these loops. So this model doesn't have any time effect in it. And so I did do a test to look at what the effects of the wind would be. And that's why we ignored it, because it wouldn't affect it. But of course, the destabilizing effects are different and would require adding time. So I am looking at adding a time aspect to this model, and then we would start to look at effects like that.
Jeffries, who asked, is the base pressure and temperature consistent with the X-ray observations of AB Dor?
Okay, so the question is the base pressure consistent with X-ray observations of AB Dor? Yes. I mean, I don't like, yes, basically all of our range of base pressures that we tested are consistent. So it wasn't something that we could really use to discriminate between models. But yeah, it is consistent. And that is actually, the X-ray data is one of the reasons that I tend to favor the higher temperatures. Because of that, we believe that AB Dor has a high temperature corona, which is why the lower temperature contours that don't agree with the others, instead of considering them, we tend to prefer the higher temperature result.
Okay, so we have talked about that. Clara again.